Yeah, let's start. Today's talk is by Xizhi Liu at DIMAP, Warwick. He's gonna talk about Hypergraph Turán problem 1 to infinity based on joint work with Mubayi, Reiher, Heng Li, and Zhang. Yeah.
Okay. Thank you. Thank you for the invitation. So this talk will be based on several papers. I mean, a long project, starting with my advisor, Mubayi, and later Reiher joined us, and later Professor Hou and his students also joined this project. Okay. So basically two parts in this talk. First is a review of what happened in the graph world. And the second part is about the hypergraphs. What's the difference between graph and hypergraph? So let's start with some basic definitions. So when we talk about a hypergraph, we have some vertex set and some collection of subsets of your vertex set. Here we will assume every edge contains R vertices. For our talk, we only use R equals 3. For graph, we use R equals 2. So here we have some simple examples. The first three are graphs. So you have 3 vertices and you connect all pairs, you get a complete graph. Here you get a K3 complete graph on 3 vertices. You have K4, you have C5. The last one is a 3 graph. You have 4 vertices, and every triangle gives you an edge. So here you have 4 edges because you can see 4 triangles. And this is usually called the tetrahedron. You can, it's simply some 3 graph on 4 vertices. The notation we use is this K4, 3. So this is the definition we will use today. So first we look at the graph. Graph meaning every edge has only 2 vertices. So the ordinary graph, you see. So a typical question people asked in this area is when you forbid some small structures, say you do not allow your graph to have a triangle, then you can ask what's the maximum number of edges you can have. This is you can replace triangle by any structure you like. Maybe the first extremal result is this Mantel's theorem proved in 1907. It answers this question. It tells you which kind of a graph has the maximum number of edges. It's exactly this bipartite graph. So bipartite graph means your vertex set has 2 parts, and you only allow edges crossing these 2 parts. And the notation we used for this particular bipartite graph is the N2. T is related to the following theorem. Here, N means you have N vertices, 2 means you have 2 parts. Okay. So it's natural to generalize this result to another family. So here we define the Turán number. So given any family F, so F is a collection of hypergraphs that you do not like. And there's a function, extremal NF meaning you forbid everything inside F, you forbid every member in F. And then you look at what's the maximum number of edges you can have after you forbidden every member in F. So this function denotes the maximum number of edges you can have. So it's a function in N. So sometimes we only care about the asymptotic behavior of this function. So we normalize this EX function and take a limit. So for example, the Mantel's theorem in the previous slide. So for this particular graph triangle, T3, EXN is this number. So if we rephrase the Mantel's result using this equation, and if you take a limit, you will see, okay, the limit is a half. In the definition now, R is 2. So it's n squared over 4 divided by n choose 2. The limit is a half. Yeah, when we're talking about a hypergraph, R will be 3. Yes, maybe the most famous result in extremal graph theory is the Turán theorem, which just replace the triangle by any complete graph. So if okay, so the notation is a bit confusing. Now R is any integer. So if you replace complete graph on 3 vertices by any complete graph on R vertices, then Turán tells you the extremal function for this clique. Yes, so it's a particular number related to R times n choose 2. Here I use n squared over 2 just for simplicity. So when you take a limit, meaning when you divide it by n choose 2, you will see the limit is this number. If you replace R by 3, you get a half. So you recover the Mantel's result. So this is for complete graph. Okay, I forgot to mention the extremal construction. So meaning which kind of graph has the maximum number of edges and does not contain a bigger clique. This the so-called Turán graph. For example, if R equals 4, meaning you are forbidding K4, then the extremal graph is this 3-parted graph. We use this notation. T means Turán. So now you can see we forbid something, we get a number, and we get the extremal graph. And the extremal graph has a very simple structure. So you might be wondering what happened in general if I forbid any arbitrary graph. And this is what Evdish and Stone studied. So to introduce their result, we need one more definition. So the chromatic number, meaning when you the minimum number of colors you need to properly color a graph. For complete graph, say for K3 you need 3 colors to properly color this complete graph. For K4 you need 4 colors, and for C5 the chromatic number is 3. So you need 3 colors. So what Evdish and Stone found is that given any family F, the extremal function of F only depends on the chromatic number of F. So what do I mean by the chromatic number of a family? say this, say you are given this family F. The chromatic number of this family is the minimum chromatic number of every member inside F. So for K3, the chromatic number is 3. For K4, the chromatic number is 4. C5 will get 3. So the minimum is 3. That's the chromatic number of this family. And what Eldish and Stone proved is that, okay, what only matters for this family is this guy. You can only consider the member inside F with the minimum chromatic number. There's some error term, little o, and we usually do not care about this. Yes. So this is the Eldish-Stone theorem. It determines the Turán density of any family, infinite or finite, we do not care. Okay. Then you can keep asking, okay, how to generalize this, how to extend this result. So people starting to ask, what's the structure of, say, a triangle-free graph with many edges? Will be the structure close to some bipedal graph? So that's lead to another classical result, usually called the Eldish-Simonovich stability theorem. It says, okay, if you forbid a complete graph and you have many edges, many means you are not very far from the extremal function, only less by epsilon and square. Then this theorem tells you, okay, give me any such G. The structure of G must be close to the Turán graph. Close means you can remove some edges and add in some edges to recover the Turán graph. And for this picture, it means you can remove everything inside this part and add in the missing edges. Then you get the Turán graph. So stability just from the number of edges to the structure. It's this type of result. So in fact, you can replace this KR by any family F. Yeah. In general, you can do it for any family F. So a natural corollary of this stability result is any family of graphs is one stable. So what do I mean by one? One means you can approximate the structure of G using only one structure, meaning the structure of the Turán graph. So everything is close to the Turán graph. Stable means you have this type of stability result. So here one means the Turán graph. Stable means Eldish-Stone stability. Yes. So this is what happened in the graph world. You know the Turán density of any family. You know the structure of any F-free construction with many edges. We basically know everything here. Then it's natural to ask what happened in hypergraph. When we talk about hypergraph, I always assume R equals 3, meaning every edge contains 3 vertices. Okay, in general, it's true for any R, but we now focus only on R equals 3. So for hypergraphs, it's much more complicated. Yes, like 20 years ago, people still asking questions like this: does there exist a finite family of say 3 graphs whose Turing density is not a rational number? Okay, why rational numbers? Because when you look at this Eldridge-Stone result, it tells you the Turing density of this family is a rational number. So it's natural to ask if a similar statement is true for hypergraphs. So this is what people asked in 20 years ago. And so it was disproved like 10 years ago by Biber and Talbot using the flag algebra and a computer. They found a family of 3 graphs, a finite family of 3 graphs. And they use a computer to calculate the Turing density, and it's irrational. And until very recently, people found a single 3 graph whose Turing density is an irrational number. So this conjecture does not care how many graphs you forbid, as long as it's finite. So this theorem tells you you can forbid only 1 3 graph to get an irrational number. This is not very related to our topic. I'm just showing to tell you again, for hypergraph, it's very different from graph. Okay, now come to the main topic. So 2 questions we care about for Turing type of problem. The first one is what's the Turing density for any family? And the second one is what's the structure of every near extremal construction? And one of the most famous conjecture is this so-called tetrahedron conjecture. It's still open, and Eldridge offered $500 if you can solve this. So let's recall what is this graph. This graph is a 3 graph on 4 vertices. It has 4 edges. And also you have this bigger triangle. It looks like a tetrahedron, so we call it a tetrahedron conjecture. So when you forbid this simple 3 graph, can you tell me the maximum number of edges you can have? This is the Turing's conjecture. And Turing gave an extremal construction, which he conjectured is correct. The construction is this 3-partite 3 graph. You have 4 types of edges. This is the first one, second one, third one, fourth one. So if you calculate the number of edges in this construction, you will find it's approximately this number. So this is the Turing's conjecture, and it's still wide open. Yes. So why is it so hard to solve this conjecture? Because what the Turing conjecture is not exactly correct, meaning except for this construction, there are in fact many other constructions which achieve this bound, meaning with this many number of edges, but with a different structure. So it's basically 40 years after Turing's conjecture, Brown found that in fact, over 3 many non-isomorphic K4 graphs with exactly the same number of edges as this construction. So I cannot show you the construction because it's a bit complicated. So this is a bronze result. Besides this construction, you have many more other constructions. This is the linear in N, but this is not the worst case. Kostoshka found that you can have exponentially many such constructions, meaning K4 free, but with the same number of edges as the extremal construction. And this is false when N divides 3. But in general, you can do it for any N. So a corollary of this result is that K4 cannot have the stability property because you have exponentially many non-isomorphic extremal construction. So it certainly has have no stability. So maybe that's the reason why it's so hard to solve this tetrahedron conjecture. Okay, so how do we describe the family without stability? That's what Mubayi and Piocco thought about like a decade ago. So when you do not have stability, can you do something a bit worse? So they defined the so-called T-stable. Let's recall what we said for graphs. So for graph, we say every family is one stable. One means you only need one structure to approximate every near extremal construction. So here is natural to guess T means you need a T extremal, you need T constructions to approximate every near extremal construction. Let's look at this by a result. Yes. What would be a two-stable family look like? So two-stable means you need two structures to approximate every near extremal construction. What we proved with Mubayi is this, you can find some finite families, doesn't matter, such that it's two-stable. So two means you need this two particular structure to approximate every near extremal construction. So if you write this in the form of Erdős-Szymanowicz theorem, it says, okay, if you give me any F-free 3 graph with many edges, then the structure of edge is either close to the first construction or close to the second construction. This is the meaning of two-stable. You need two structures. And yes, so yeah, so people know the existence of T-stable families for any T greater than 1, like only 2 years ago. Okay, even though they defined this T-stable like a decade ago, but they do not know if such family exists. So in general, you can do it for any T, not just for 2. Like you can create a 3-stable family, you can create a 4-stable family for any integer you like. But there is no picture to show the structure of this T-stable family. So the idea is how to create this T-stable family. So if you look at this second construction, so the picture is for the complement of the graph, meaning you remove from a complete graph on 6 vertices. You remove these 4 edges from a complete graph on 6 vertices. So if you observe, if you look at this graph that you throw away is actually two regular third graph, meaning every vertex is contained in two edges. So using the same trick, you can first take T complete graphs. Say the first one on N1 vertices, and the second one on N2 vertices. Firstly, you fix this T complete third graphs. Then you remove some regular graphs from this complete graphs. After you throw away this regular third graphs, you get the T extremal constructions. So that's how we create this T extremal constructions. After you find this T constructions, then you define your forbidden family. So it's kind of cheating. So usually people find a family, then calculate the Turán density. Now we find the T extremal constructions first. Then we define the forbidden family according to the structure of these constructions. So the theorem says, okay, there exists some finite family for any graph that is close to the extremal with many edges. Then the structure of G must be close to one of the following T constructions. Yes, so that's how we create a T-stable family. But for our definition, we do not require T to be a finite number. So, so it's natural to ask if there exists an infinite stable family, meaning, okay, can you find infinitely many extremal constructions? So the answer is yes, for sure, because of this tetrahedron conjecture. It has exponentially many extremal constructions as the n goes to infinity. Yeah. So if you can prove the tetrahedron conjecture, you find an infinite stable family. But that's too hard to prove. So yes. So what we did recently was find another approach to create a family that is infinitely stable. So infinitely stable means you need infinitely many structures to approximate every near extremal construction. So what's the method to construct such a family? So it's the idea is non-minimal hypergraph. I will explain this later. So it's a very simple operation. So for example, if I take a complete graph on 4 vertices, and yeah, the first idea is if I take a complete graph, a complete 3 graph on 4 vertices, I can find some family F. I can find some family F such that the extremal construction for F is the blow up of this 4 vertex 3 graph, meaning every extremal F3 graph has this structure. And this is known for any finding graph F, not just for K4-3. Given any graph, I can find a finite family such that the extremal construction for this particular F is a blow up of this graph of this graph. But this only gives you one extremal construction. So how do you create infinitely many from this? So what we found is that if you twist this key-fold free a bit, then you can find infinitely many extremal constructions. So what is the operation we find? So we call this operation crossed blow up. Yes. I already mentioned the blow up. Blow up means you replace every vertex by say n vertices. Then you get a 3 graph on 4 n vertices, and you add all triples that was there before. So it's basically you clone every vertex for n times. So that's the definition for ordinary blow up. What is the crossed blow up? So crossed blow up means, okay. Here is our tetrahedron. You can do it for basically any graph, not just for this forward vertex graph. So I blow up this graph in the following way. So first I copy 2 and 3. Let's label this 1, 4, 2, 3. This would be 2 prime and 3 prime. So I add 2 new vertices, 2 prime and 3 prime. And the triples I add is this one. So first you have triples that contains only one vertex in 2 and 3. So if you look at these 2 triples, it contains either 2 or 3, but not both. So we keep these triples in this operation. Meaning if you have only one intersection with 2 and 3, then you are fine. You are still in this graph. But for others, if you contains both 2 and 3, say this edge, then you need to change a bit. For example, this and this big edge, they become this guy. For 1, what we did, so here correspond to this edge. It contains both 2 and 3. Now it becomes 4 edges, meaning you have this, you have this, yes. So one is joined to every pair here. So now 1, 2, 3 becomes 1, 2, 3 prime, 1, 2. So one edge now becomes 4 edges. This is for vertex 1, and for vertex 4, meaning this edge, it contains both 2 and 3. It also becomes 4 edges. But we twist it a bit. So it becomes this 4. Okay, let me change another color. They become this 5 edges. Yes. 4, 2, 3, 4, 2, 3. Yes. So the link of 1 is a complete graph, is a complete bipartite graph on 4 vertices. The link of 4 is also a complete bipartite graph on 4 vertices, but they are not the same. We rotate it a bit. Yes, so that's the meaning for crossed blob. So what's the difference from the ordinary blob? If you for vertex 4, you do the same thing for 1, and you recover the ordinary blob. Okay, with these 2 edges. And for 1 and 2, you add all these triples. This is the ordinary blob. This is the crossed blob. So that's the only difference is you rotate the link for 4 a bit. Okay, why we can get infinite many constructions from this operation? It's about a property of this new graph. This new graph is non-minimal. So meaning it has the following property. Okay, now I have a 3 graph on 6 vertices. If I blow this 6 vertex 3 graph up, say I blow up in the following way. So now we consider the ordinary blow up. Given this, so we can forget everything else. By looking at this particular 6 vertex graph. The property it has is the following. It will blow up in the following way. It will blow up vertex 1 into n over 4 vertices, the others into n over 8 vertices. And calculate the number of edges. You will see, yeah. Yeah, I don't remember how many edges. It's approximately, for just 2, 6 over, yeah, anyway. So it's basically equivalent to say you are blowing up this, your original graph. These 2 guys have basically the same number of edges. Sorry, this one. This is what happened for this 6 vertex graph. Okay, after you blow up in the following way, you get this many edges. But the structure is still, unique because of the numbers you're choosing is unique. So non-minimal means you can blow up in other ways to get the same number of edges. So you will blow up in the following way. you still have the same number of edges. This can be plus delta. Yes. So if you blow up the 6 vertex 3 graph in the second way, in the following way, you still get this many of edges. Delta is any real number between 0 and 1 at. Yeah, you can get. So the meaning is if you change the size of this diagonal pair, if you shrink the size of this pair, you do not change the number of edges in the blow up. So that's what we call the non-minimal, meaning you can blow up it in different ways to get exactly the same number of edges. So where is the infinite now? So what is our infinite construction? Infinite is here. You have infinitely many choice for delta. You can blow up it in infinitely many ways to get the same number of edges. So our extremal construction would be look like this. This will be one of our extremal construction. This is also one of our extremal construction. And in general, you can take any blow up. So this is what happened. You can take any blow up of this 6 vertex 3 graph, and it will be our extremal construction. So now you have infinite many extremal constructions. Whether is the forbidden family, you can forbid any 3 graph that does not appear in these constructions. I'm going to draw it like this. And F has say 100 vertices. The 100 is not a curve as long as it is finite. So the idea is to find some non-minimal. First step is to find some non-minimal 3 graph, and the way we find this non-minimal 3 graph is using this operation, the so-called crossed blow up. It's a non-minimal means you can blow up it in different ways to get the same number of edges. So that's the property of non-minimal hypergraph. So first step 1 is to find such a graph. Second way is blow it up in different ways. And the third step is to define your forbidden family. And then you can do the trick in Hypergraph Turán problems to prove for this particular family, the extremal constructions are exactly this follow-up. And apparently you cannot approximate the structure of these constructions using any finite, using finitely many structures. Because the size of this part can be any number, any real number. Okay. Yes. So that's that's the last result we have. Any questions?